Yeah, sure. Yeah, I need you to close the door because I can hear myself otherwise. Yeah. And the reason why the DeepSeek math paper is particularly important, right, is that the previous time around when we went through the DeepSeek R1 paper, we essentially kind of just skimmed this through. We skipped past this, but the DeepSeek team credited the DeepSeek math paper as one of the key things behind like creating the whole reasoning data set and things like that. There was a lot of emphasis on the math and math data set as being the entire path of how they achieve R1 performance. Well, the paper itself covered more into towards the technical aspects of like how they got it to scale, how they got it to train that far. This is more of like their previous math model that formed the foundation on how they built the data sets involved for the reasoning training. So, this is a much older paper, and what it covered was a 7B math model, which at that point of time when it came out, right, was literally one of the best math model out there for its size. In fact, outperforming even at that point of time, even like some of the GPT-4 APIs, though, if memory serves me right, then GPT-4 updated itself to like be better than the math model. So, but for a period of time, it was better. And what was more exciting is actually for those who were at Kaggle, literally for a very decent period of time, this model just dominated all the math contests in Kaggle. And this is literally the how they did the pipeline to build the data set, which based on their responses of for the DeepSeek R1 papers and some of through Twitter and some of them through the interviews, it's responsible for how they actually build up the data set subsequently. So yeah, this is the performance there. So introduction, yada skip. Okay, so here right, they cover the first step right, and the challenges is actually to build the data set that is focusing on math itself. So there are existing data set like open web math, and things like that, but it's for most part insufficient. So this is really more this first part is more of like a data set paper actually, and what they did right, what they did essentially right is that using known good math sources, yeah, known good math sources, right, they actually scan common crowd for relevant math articles, papers, and so on. And this is what they use for the pre-training of the math-based model, including existing math data sets. And wait, I think I'm remembering it out of sequence. Where was it? Yeah, data collection decontamination. So here it is. So when they went through here, right? They started with 500,000 data points off for the web corpus there, as a positive training example. So these are known good examples. And then subsequently, right, they did the embedding search, so vector dimension uh, on that, and they basically use the existing models, right, to crawl through all the common crawl pages to find the relevant math domain papers to filter down the data set. The Obviously like to crawl the entire common crawl is with AI models is not practical. So what they did is that they require at least a match to one of the n-grams of three words. So they use the existing good data set. So the minimum number of word occurrence to three. Oops, accidentally tap that accordingly. And and they use that to filter the data set respectively. And this is what they did for the base math data set. And then subsequently that resulted in 40 billion pages. And then subsequent and once they started using that, right, they subsequently used this to train the model. So yeah, skipping over that. There's also a whole segment regarding benchmark to avoid benchmark contamination. So this is back to like the n-gram filtering out techniques respectively as well. So yeah, and then subsequently, like when they try to, it covers the training settings itself, um, fairly standard. But what 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 was interesting is that for them, right, they found that the downstream performance subsequently when they did train the model pretty much outperform every other math data set prior to that. And if from a token to performance perspective, because of how they thoroughly deduplicated and try to curate a diverse topic. Subsequently,
Eugene, can I stop you there?
yeah.
One question. So was this the reason because they got a better data set where they saw the thing blow up, or was it more of that they improved the training part of it and that's why the model started to show up?
So right now, previously, right, so you have to see, right, this is actually a fairly standard model. This is not a MOE 256 model. So this is just purely data set. From a point of view of data set. Even the parents that they shared previously, it's a fairly standard thing. So hypothesis, I mean, this one I'm actually need to go through the data set to double check it. Would be actually for the one of the reasons why they did the search and scan through the common crawl and filtering, right, for those math concepts, right, is that if you take existing math data sets, which tends to be like, let's say, using one of it is a filtered set of ARXIV papers. It tends to be math data that is a little bit overfitted to a certain framing or style or narration. Well, they wanted just a lot more data on math in general. So this is literally I guess in a sense, a diversity and web scaling of the math data set. Does that make sense?
Mm-hmm.
Yeah. I think I will need to double check this, but like it will not surprise me if like random Reddit discussion about math suddenly appeared in the data, things like that. So that part I definitely need to fact check because I have respectively. But the idea is that it allows them to go beyond what's the existing sources. This is no different from actually existing techniques per se, but I think it's more of like no one really bothered doing it for math, so focused prior to this. So yeah, that's what I did. But I think the next step, right, beyond that, right, it's where is the important part where it's the seed for R1 is here. The problem solving step by step reasoning. So they started doing the chain of thought prompts respectively, and because math is easy to validate code wise, like you can validate that the generated result matches. They can rinse and repeat that respectively. So this is where the original seed for DeepSeek R1, which at that point in time before we call it reasoning, everyone just calls it chain of thought. And essentially they prompted the model, they generated the data, they validate it, and then they repeat the process respectively. So this is how they bootstrap R1 essentially. So and then subsequently they cover like training, introducing tool use, and then subsequently they prompt the model, and then if they get the result, it reinforces itself. You have to understand that this part, right? Well, they did have some humans to like validate and check stuff, right? The big thing here, right, was that this is fully automated for most parts. So this is how they bootstrap their reasoning data. Without, I would say, at that point in time, because these reasoning models wasn't even a thing yet for OpenAI, without needing OpenAI to generate all this reasoning data for them. Because at the end of the day, math is math. If the model gets it right, provide formal proof, it succeeds. So they subsequently repeat this with other domains from what was understood, and then that lead to what the current reasoning models that we have. But even then, they said a lot of it is just based on math and it's scaled accordingly. Currently, there's a coordinated open source effort throughout multiple groups, right, that essentially use this paper as reference and the DeepSeek R1 model to try to create reasoning data sets for math and code. Because code is similar to math in the sense that it is easy to validate. You can generate the code, check whether the inputs and outputs are matched, pass, rinse and repeat. And yeah, and I think what is exciting is that if this is the case, and if this is really what is all that's needed to build reasoning data sets for R1, at least as claimed by DeepSeek, it means, right, they literally gave us the blueprint, right? And the rest of the community right now, as you can see on Hugging Face, etc., are creating a data set. It means an R1 data set will be created. If there is an additional secret source that's needed, which the DeepSeek team claim there isn't, then it's something that we'll find out in time. So yeah, that's why I say this is kind of like a prerequisite paper to R1, and it literally helps show, right? If you look at the date itself, right? This was when, what was it again? This was April 2024. So they've been so for a lot of people who keep thinking R1 is a sudden thing, right? These are things that they've been building over time in the background to where it is today. I think what is interesting here is that because the way it's done, right, is you have a hyper specialized model focused in one domain, beats out GPT-4, for example, and then you take that data, train it on a much bigger general model, and then that's where it starts learning how to apply in other domains. In this case, you can't prompt this math model for medical advice, for example. It never learned medical advice, doesn't even know what medicine is properly. So yeah. Any questions on this part so far? I'm not sure whether you want to cover GPRO, PPO, but I'm not so sure whether that's the most important thing about this paper, actually. That's in my opinion.
And
Eugene,
go with 7B. Sorry.
Okay.
7B, why did they choose 7B? I mean, did they play around and come to 7B? Or they thought that was good enough?
Honestly, my gut feel was that because if you remember this at Kaggle, right, there were already decent math model at 7 to 12B to 32B size. So it's already been proven like a 7B model is good enough. And I think for them, this was just an exercise of just like finding the smallest, cheapest model that they can train that can get the job done at a good enough performance. They might have done abalation, or maybe they just picked it. I honestly don't know. It wasn't covered in the paper why they picked 7B, but it's an educated guess, I guess. I think it's a reasonable choice. The alternative I would have done would probably be the 12Bs, because that was fairly popular as well. The 12 and 14Bs. It just boils down to they only had small GPUs. I think that's another way to view it. Yeah. Okay. So yep.
so Eugene, I had a question. I haven't read this paper yet. It's on my list. I was actually thinking that they were gonna say they use synthetic data generated by like Lean or another theorem proving language, right? Like I'm really surprised that they didn't leverage MathLib and like all this stuff, because there's been a ton of work on theorem proving languages recently, and it seems so obvious to me. And I wonder if there's a reason why that's not being done. Do you know anything about this?
I don't think we can double check it, but if I remember correctly, they did include other math data sets as well into the mix. So it doesn't mean what they did was to basically add more outside the existing data set. So I don't think
Yeah.
they excluded it, but I'm not so sure whether they added
Well,
those microprogram languages.
So like no, what I mean is, oh, I see. Okay, they could have used like MathLib itself. Yeah, that makes sense. Okay,
In fact,
yeah,
they
no, that
cited a
makes sense.
few
Yeah,
math data sets that they used previously. I apologize that I'm trying to figure out how to best use my phone in this scenario.
but like if you told me, okay, RJ, go create a math model, I would of course kind of copy what they've done here, but I would also just like have a model generate proofs, interesting proofs using Lean, right? And then I would and like sort of use that as synthetic data set to train the model, because I think that like that will show the model how to do like proper proofs, right? So that you don't have to bake in the logic of the proof into the model, like you're just doing it through the data set, but that you are proving proper reasoning, or you're creating proper reasoning steps that are verifiably correct.
Yeah. So proof wiki is in there. So
Okay, yeah,
yeah,
interesting. Okay,
it
so
may
maybe
not be
that's
the
enough.
exact data set that you quoted, but
Yeah,
conceptually it's
okay.
there.
Yeah, maybe
So
it's okay. Yeah, and maybe proof wiki leans on, no pun intended, leans on Lean. Okay, yep, that makes sense.
So yeah, yep. Is there any other questions for this segment? For I think like subsequently the GPRO PPO, I don't see when I read through it, I don't see anything that is like I would classify as an innovation there. It's just kind of like we made the data set, we taught it how to use tools, we improved on the data respectively, and then so in this case, reference model then got the reward. It found out that the proof is valid, train it again, rinse and repeat. I I don't see anything new in here unless I missed it. I apologize because I only like skimmed through the paper in like half an hour prior to this. Yeah. If I missed something. Okay.
There's a claim that GRPO is much more efficient than PPO. The way I do PPO is have the same network kind of give you the value function and the policy. So I don't know why they claim GRPO is more efficient.
Oh no, I think I saw that phrase. I know which one you're referring to. I would say if I remember the exact wording was where were you? Do you happen to know where the line is?
You just passed it. I mean, they say it's more effective and more efficient, but I think in more recent papers or in the R1 paper, they push on the efficiency even more. So
I think another thing to consider is that when they say efficiency, right, they are also probably taking into account the VRAM overhead and the compute overhead rather than because here's the at the end of when you're compute constrained, right, your consideration is not one thing that strikes me about DeepSeek and this is very similar to how we operate the other KV group as well is that we are not research purists per se. If you're research purists, right, you'll be like, hey, if one token step PPO versus GRPO, PPO is better, then GRPO is worse, like per token step. Like if you're research purist per token step. But for DeepSeek and for us, you'll be like, if GRPO takes half the RAM and compute, VRAM compute, even if it's not as efficient, given my compute budget, it is more efficient. You get what I'm saying? So I don't think it's a contradiction there per se. It's like the struggle here is because they didn't show abalation. This is how I interpreted their claim. They found it more efficient on your hardware, and then they proceed with this. Rather than this is GRPO is more efficient than PPO given the same amount of steps. Yeah, it didn't sound that way.
Eugene, I thought when we were covering the R1 paper that there was some discussion of how they didn't need the value model, and that was why it was more efficient.
Yeah, just
if you look at the diagram of
wait.
PPO on page 13.
Exactly.
Yeah. So there's that value model on the PPO side that's not on the GRPO. I thought my understanding was that was the thing that GRPO allows you to use the average of the group instead of having training a value model, and that was where the efficiency increase came from.
Yeah, so like once again, if you read based on their language and how they think things through, right, significantly reducing training resource. So
yeah,
it's like less VRAM. But you have to remember that they are they are not GPU GPU poor. They are not exactly GPU rich like the big labs. So
but
these are
my
actual
point is in other networks or you can kind of use a common trunk for the policy and for the value model and just have two prediction heads, one that predicts the policy, the other one that predicts the value. So like that, you don't always need two models. So I wonder if the usual setup is two models or one model that's multitask for these RLHF models. So then the claim that you need just one model here, it's a bit exaggerated because usually you may use a multitask model for policy and value. I mean, you can see in some older RL papers that yeah, they have 2 prediction heads instead of 1.
That's a good point, and I think we're entering the speculation area because likewise also like some of the previous papers I've seen, it's 2 models as well. So yeah, maybe you're right. Maybe just using single model, 2 heads or 2 even like extra layers and head would have similar effect, and we have done that cost savings and training resource savings. As to why they never tried that, or maybe they tried it and it didn't work, that one we have to ask them. Yeah. I think there's one thing that is in very repeated fashion for DeepSeek, right? One thing that is always missing, right, is the abalation on how they did things. So if I were to have a criticism, which to be fair is not fair to them because everyone else kind of like releases even less details than them, is that they'll be like, we did this is what worked, this is the path. Then when I have these questions like, why didn't you try that? Then we don't know whether they did. That's a problem. Yeah.
So the other thing with Honeki, when he said about the mathlib and lean, DeepSeek prover actually used it later on. So that's what it says.
Okay. This wasn't meant to be a deep paper. So is there anything else that we want to cover? Yeah.
Can I just check my understanding? Oh, whoops.
Yeah, sure.
That. So even if you had a single model with multiple heads, you'd still have to do the computation and the training on it, right? So it would save something there, correct?
VRAM at least. It will save
Yeah.
VRAM.
It should also save compute. It would also save VRAM, but I think it should save some compute. Am I misunderstanding?
I mean, usually when you have multitask, the compute part is like 2 prediction heads that are different. So like compared to the big trunk of running the
Got
whole
it. Okay.
versus end to
Makes
end,
sense.
it should be
The head is a small number of parameters relative to the size of the
yeah,
trunk.
but it seems my understanding is wrong because they claim so I would do it with the multitask, and I saw other older papers in non-LLM setup where they use 2 prediction heads. So I was wondering why they haven't tried that here, or if that's not the way to do it in LLMs or in RLHF.
Okay.
I'm willing to say it could very well just be the case they never tried. So
Okay.
we have to ask them. Like this, I think this is generally, but conceptually, it will save VRAM as well. The data goes in. Yeah, it just goes through. They don't need to backward pass this. So yeah, it isn't that much more compute as well.
Okay. It does seem, I'll just say, amazing that we've got a whole model in one case, and then in GRPO they're like, let's just do a Monte Carlo average. That just seems like, oh yeah, why didn't somebody else think of that? But anyways, we can move on.
It seems they can run for the same prefix, they run more completions, and then they get the average. My understanding is that in PPO, you just run 1 completion, per example, and then you score that completion. But if you run 128 things at the same time, maybe you get like more signal. So there's some trade-off in like reusing the prefix and generating more things versus just using 1 prefix at a time and scoring it. And I don't have a mental model what the trade-offs are between the 2. And
that was going to be my question. Okay, thank you.
Yeah, but I think down here is just more of like for each prefix there's a multiplier effect. Well, in PPO, you have multiple individual prefix, but at the end of the day, PPO is still trained in batches. I mean, if not, it'll be too slow. So it's just, yeah, I think it's just about it still needs to go through
but
all
here
those.
they have a batch of a few prefixes, and then for each prefix they generate a few outputs. So it's kind of like, I don't know, I work in recommender systems, and we would have pointwise learning where we would learn from 1 label, like 1 click or 1 not click, and then listwise learning where we look at the entire request and see which result was clicked and propagate based on a set of results. So it's kind of the same, like in group RPO, you propagate signal from more things, some positive, some negative, and you also average them out. But yeah, it's kind of interesting to think about, but I haven't figured out exactly why one is much better than the other.
Okay. This does give me a little bit to think about as well on that. Yeah, because I did never really considered it too much, because I think for me as well, like for us, right, we always tend to lean in on, if it's cheaper resource, that's all we care about actually. Yeah. So yeah. Okay. I'll move on to the next paper. Forgive for the buggy switches. Okay, let's see. Yeah. Anyway, for those who's wondering, my laptop is like in an infinite login loop with um
Yeah, Eugene, I'm sure you are not aware of that, but the speaking attendees picture keeps popping in front of us and hiding.
oh, I
So-
can get rid of it now. Yeah. Thanks.
Okay. So I shared how you can block it with the options.
Oh yeah. It's just that I have no
Yeah.
means to open that without sharing the
Yeah.
screen. Okay.
No. Even while you're sharing, you can go down to the options more and select the host option and hide the old profile pictures. But
Anyway,
yeah.
are you able to see
Thanks.
the Mamba and the Llama picture right now? Just making sure.
Yes.
All right.
Perfect.
So DeepSeek R1, like I said, there are multiple teams trying to replicate the data set based on that math paper, and then subsequently on the R1 model itself. So that is like one road to reasoning data set with OpenAI. I'm covering the other paper that I'm covering is Mamba and the Llama, because for those who don't know, we did a similar process, modified based on this paper. The authors of this paper are very well aware about what we did, because we collaborated notes for our upcoming paper as well, and essentially we made, this is not the name of the paper, the RWKV in the Llama, or in this case, the RWKV-in-the-qwen. Using several of the concepts from this paper, and we modified respectively how to modify an existing transformer model to a linear model. We launched our 32B model at NeurIPS, and a little bit of a spoiler, we are launching our upcoming 72B hybrid version of using the altered version of the techniques that we did previously in the next few days. So that's why I'm going through this paper. Okay, so for most parts, there's a lot of things in here, right? Literally, because this paper is talking about retraining a model while retaining most of its benefit at a really low budget, and changing the attention mechanism, right? You can actually search and replace Mamba with RWKV. In concept, you can search and replace it with XLSTM and Titan and etc. Because conceptually, the technique will work the same. So the idea here is that you take an existing transformer model, and essentially you freeze the feed forward network layer, because where were you? This is explanation what's different between RNNs and transformers, but okay, here it is. Okay, so at the end of the day, right, all transformer models are attention layers, feed forward network layers. Then you have the embedding, and then the output heads, and subsequently, right, what you can do is that take an existing pre-trained transformer that's, let's say, 15 trillion tokens trained, freeze the feed forward network layer. So this is similar to what they did, hence the eyes there, the freeze logo. And then subsequently, you delete the attention, and you delete the attention layer, and then subsequently you add in the Mamba layer, and then you train it respectively. And what we realized, when we did the same thing for RWKV, is that this is actually incredibly cheap and fast by AI training standards. to put into illustration, right, our upcoming 72B model, right, well, we started with 2 MI300 nodes. We essentially made improvement to the VRAM technique stuff. Basically, we optimized our training code to the point where we ran the whole training process again. We were trying to replicate the model on a single node. So we were able to successfully convert a transformer model, be it 32B and 72B, to a linear model with some loss in MMLU. But given the amount of tokens that we trained was like, it was only a few hundred millions, right? There was no way for it to actually learn new knowledge, given the very limited data set. So one of the derivative for this paper and based on likewise in our replication was that it's actually leaning into the conclusion right now that majority of your knowledge, for the lack of better words, right, is actually only in this feed-forward network layer. And the attention layer is just more of like being able to pay focus on things. To quote one of our teammates, right, the way they frame it is like, if the FFN is the knowledge, right, then the attention layer is just basically the part of the brain that lets them pay focus. And when they reset the model, right, it's as if the person has ADHD and just can't focus. So us doing that limited training is basically fixing the nerves to essentially allow them to pay focus again. And that's why something similar to here below, I believe they did cover MML, the scoring. No, so speculative decoding. I'm going to skip the speculative decoding part because that's not the point of this paper. Is that they subsequently showed that as they convert it, and then with different ratios of linear layers to transformer layers, it's able to actually retain quite a large percentage of the transformer level performance. So this is empty bench. Like for example, you look at the Llama empty bench, the baseline is 8. And then subsequently as they splice in, it's around 7.7. For likewise, we have seen similar things. I think the better examples below. So for example, 50% is 7.32, 6.74, 6.48, 5.64. 5.64 is basically pure Mamba. There is a slight performance degradation, right? There is a question of like, why do we bother then? Because this makes the model slightly dumber. I think the key thing here, right, is it's all about trade-offs here. One, right, is that while it is slightly dumber, the computational cost is substantially cheaper. So for example, right, even at like 50%, right, at 50% mixed transformers to basically state space / RWKV / whatever it is, right, we are looking at easily cutting the VRAM requirement by close to half, because essentially the RNN models, especially over longer context length, right, their VRAM requirements are essentially rounding error for the layers. Another thing which is not covered in this paper, which we actually managed to further dive deeper into, right, what we realized is that in the trained transformer layers, because we experimented by replacing different layers one at a time and basically Frankensteining it various way, right, long-term attention, right, is actually mostly done by the upper layers. Well, the lower layers don't actually impact much on long-term attention. So once we realize that, right, it means that the lower layers, right, you can safely do the conversion, right, while still maintaining stronger longer term attention scores. And this is reflected, right, in this paper as well. Likewise, when we go further down in here. So if you see respectively, right, this is the very classic needle in a haystack test, right? Needle in a haystack test, right? Even with their in one of their models, right, even though it was converted with 50% train, right, it was able to, for most parts, pass the test. I know there's like some issues here. What we realized, right, and this I don't think it was covered in the paper, right? It was that what we realized during our replication, right, is that these segments, right, well, a lot of it looks bad, right? When you actually look at the exact needle in the haystack result, right, the model was doing things like, for example, the test number was like 2001. The model was answering 2000. It was like getting like slightly off by one digit errors kind of thing, which was promising because what it meant was that it means there was a little bit misalignment during the conversion process, which is to be expected because we literally Frankenstein these things together. So one of the things that we did in addition to all of this, right, was that after we did the conversion, right, is we did additional training to, for the lack of better words, we heal the layers together, and that actually improved the needle and haystack performance, respectively. Whether that will be replicated in Mamba, that one we'll leave it to them after we share our details with them again. So there's a little bit of back and forth between both groups right now, actually, when it comes to like these kind of details, respectively. So yep, and that's about it. Yep. So it's exciting because if everything we hear work as planned, this technique conceptually will apply to any transformer model. And even if let's say you want to retain most of the performance, you could literally just convert half and with no substantial loss, and then subsequently have that savings in compute. So it just means potentially just cheaper inference in the future for all models, including potentially the DeepSeek model, etc., etc. Yeah. Yeah. Any questions on that?
So yeah, you didn't mention it might be in the paper though. So why so few tokens for training? Like it wouldn't help to improve the performance on MMLU or whatever if you just trained for longer?
Uncertain because it's just, especially in the case of like the larger models, at least when we were experimenting for the 2B, we just didn't have the budget.
Oh, okay. So you trained as many tokens as you could.
Yeah. So we did train on additional tokens. It did get better, very slightly. The long context range performance also got better. And then we drew a trajectory, and then it was like, okay, this is going to take forever. Which is like, to be fair,
Yeah.
right? That is how it's supposed to be. So it's
Yeah.
so it's just more of a shortcut for like, if you want to view it this way, right? This, in a way, it shortcuts. I'm doing very roughly. So if I say, the training curve of 15 trillion tokens, this allows us to shortcut the first 1/4 of the 15 trillion tokens to half, depending on the percentage ratio.
Okay. Yeah. So did you does your paper that you're about to release, does it have that training curve in it? I'd be super interested in that.
So yeah, that paper hasn't been written yet, and that's why I'm
Okay.
reading this paper. So when Sean asked me, can I cover a paper? I was like, okay, yeah, can I just cover what I'm reading because I'm reading it anyway.
Yeah.
Did that make sense? Yeah.
Yeah. Awesome. Thank you.
Yeah.
So Eugene, how does this work? You just replace the attention layers with kind of linear layers, and the linear layers are randomly initialized, and you start from scratch, and they learn pretty fast.
Yeah, the most important step is you need to freeze the feed forward network layer, at least for the first stage of training. So I think what we extended on is that we changed the process into different stages, and we found that to be more reliable. And we are quite certain about this because we have repeated this process at least 100 times on the 7B model at this point. So what we did is that we freeze the feed forward network layer, similar to Mamba and the Llama. We train the attention layer. But the trick is that instead of training on the whole model input and output, you just train on the output for the original attention layer. So it's like it's essentially like you just do that one layer, you forward, take that output, take that instead of training on the logits.
So your layers are previous attention activations. So you're trying to match the full attention with the linear attention.
Yeah, we're trying to match the hidden state output, essentially.
Makes sense.
And it worked. And if anything, right, between both teams, we were like, this works way too fast. And right now, right, for us, right, the beauty for this technique, right, is that because we don't need to invest a huge amount of money into the training the FFN layer from scratch, this actually allows us to iterate on the attention layer experiments on the chip. I'll just use air quote chip here because we're still, to be fair, we are still using an MI300 server. So it's not exactly that cheap, but it allows us to iterate without doing the full 2 trillion token strain in a very rapid fashion. So and yeah, we have modified the RWKV mechanism in our upcoming hybrid model because we found it to be better. Yeah. It just allows a lot more experimentation. I think that's one thing that was exciting about this technique when it comes to experimenting with linear attention. And yeah, I do expect newer
Nice.
state space attention mechanism as well.
In terms of data distribution, do you have to train on some specific data, or you're using some random sample, or because I guess the attention path, it might matter to match the attention patterns of the pre-trained data set.
Yeah, so that's the tricky thing because I think both of us we use DCLM, which right now is considered like quite a good data set that's refined. But the issue for me was that at the end of the day, we have absolutely no idea what's the exact data composition for Llama and Qwen. So there could be better data sets. It's just I don't know.
Makes sense. Thanks.
Yep.
By the way, the view, I'm still on screen.
Yeah, I only put it open because I was trying to respond to you. Yeah. All right.
Thank you.
Yeah. Is anyone else? Any more questions? I got 10 minutes, I guess. All these are all very short papers. Oh.
Yeah.
Okay, so it looks like I'll just kick in the bonus paper, which is the bonus take too much time. Text diffusion. Okay. The reason why I say this is to me this is a rather exciting paper in a sense that this is the first large scale text diffusion model at 7B in size. But it's also a very boring paper because it's just basically we scaled up, it matched the scaling expectation and it works. So yeah, for those who don't know about text diffusion models, the general idea, right, is similar to like image diffusion where you have your prompt and response, your image, right? But then like it token by token fill it in, but it doesn't necessarily needs to fill it in sequence. In fact, I think their GitHub, right, has an example where they literally just showed. I don't think I have it in here and I can't remember where the GitHub is. Where they showed, right, the text appearing at different times, not necessarily in linear order. I think the big thing is that for this, right, because I'm just always trying to shout out alternatives, be it to RWKV, to maybe this tech diffusion architecture will end up killing RWKV and anyone else. Is that it worked, and then subsequently now they are experimenting more into like scaling it to different directions. One thing that is interesting about this technique, right, is because since it goes in a very repeated and iterative fashion, it did much better than all existing architecture, right, on the reversing test. So for those who don't know, the reversing test is that I ask it to put in a text and then I ask it to reverse the text. A lot of models tend to do it badly, in part because reversing tokens is not an easy task as well, because it depends on your tokenizer. But the diffusion models, right, text diffusion model, according to this paper, because they never released the weights, so we can't verify, didn't have any issues with it. And that was one of the things that they observed. Beyond that, until they released the weights, I don't really have much reasons to doubt what they put in the paper here, because they were very transparent. Some things did bad, some things did good. They did and yeah, it's a boring paper beyond that, other than the fact that it works. So yeah. The reason why I'm excited over text diffusion, and this is my extra thing, is that, which they didn't do in this paper, was the fact that, let me go back to Zoom and stop the screen share, is that my speculation on text diffusion, right, is that if we do it right and we scale it correctly, right, we can start testing multi-epoch training. And why I think that's important is that if you remember the previous, all existing transformers, linear models, whatsoever, we have the same weakness that when we train on the same data set multiple times, our model suffers, the multi-epoch problem. If you are familiar with image models and diffusion models, that group trains over the data set thousands of times, and the loss still goes down. And there's something about it that we don't understand that allows that class of models to do it. And for me, text diffusion models might be a way to unlock the understanding of how can we do multi-epoch training. Because if anything, humans are fairly multi-epoch trainable. If anything, we train by repetition sometimes as well. So this to me is a important research step in overall to figuring that out. Yeah. Okay.
The question to Eugene: when you do the multi-epoch training, can you always say that it improves, or it could suffer also? Is there a way to say that you're doing better versus not better?
Yeah, it's laws, benchmarks. It tends to end up creating a weird overfitting problem for transformer or even linear models. In our internal tests, which I think some people disagree with, is that we found that for most transformer models, it tends to break after 3 or 4 epochs. For RWKV, it tends to break after like 6, 7 epoch. Not really a big win, because it's like yeah, it's still breaking, unlike diffusion model, thousands of epochs. So that's to me the real goal is to really like go to that like much larger direction. It also will make it easier for if we can get this right, it'll make it substantially much easier for like fine-tuning tasks related, for domain specific or even like company specific stuff. Because if you can retrain it 1,000 times without any issue, right? When you're trying to refine the model, you can just add data, retrain on your company data again, and yeah, sure, it's not a problem.
That's exactly where I was coming from.
Yeah. It's one of the things that, for example, you train on your company data, and then let's say your company policy half change or only few paragraphs train, and then you train it again, then the model goes crazy. It's a very annoying experience for fine tuning. Yeah. So yeah.
How are these diffusion models different from BERT?
Okay.
How are these text diffusion models different from BERT?
I think the key thing for the text diffusion model is that one, when the attention mechanic is applied, right, for the individual token, so you can like freeze the prompt. So it's like prompt then completion, right? So imagine it as like pixels in the diffusion model, like your traditional diffusion model, right? These pixels or these tokens, right, it's allowed to pay attention in all directions. So that's my speculation, is that's probably why it's able to do the reversal test very well, because it's able to like through multiple steps, hey, the text there is that character, then I can reverse it like pairwise in a sorting direction. That part didn't really surprise me, and yeah, So I think that's the big benefit there. Is other than that, it's essentially just like more towards transformer diffusion models with just a much wider attention range. If that makes sense.
Yep.
But as a set threshold for masking, and text diffusion is an activity process. I think. Yep. I think that's one way to frame it as well. Correct. Yeah. Sorry. Why am I in self-driving mode? Oh, because I put my phone by the side. Leave self-driving mode. Oh, no. Okay, sorry. Yeah. So I think like to be clear, like this diffusion model, right? Diffusion text models is not a very popular path in particular because you need to go through that multiple iterative steps. Like, so like if you want to generate like 30 token, the whole completion, right? You need to like as per diffusion do 100 steps. So that doesn't sound great. But if let's say your completion is more than 100 tokens, right? It might actually be more efficient than a transformer model. The issue at hand is like sometimes when you're doing answers like ChatGPT style, you don't actually know the amount of tokens. Yeah. Okay. Yep. So yeah, I think we are towards the end of the session. For everyone else, next week, this week is a little bit hectic because like a lot of the key members for this latent space Discord is kind of like in New York, including me, for the latent AI engineer summit. If any of you here, shout out. We'll be probably glad to meet you around here at New York. Beyond that, for next week, if anyone has any papers they want to volunteer to, please drop a message into the channel. I saw some people added stuff into Slido. Yeah, but you added yourself as anonymous and saying you might be able to cover the paper. I have no idea who you are in Slido because you're anonymous. So yeah, if anyone wants to cover the papers that they added in Slido, please do so as well. Other than that, yeah, same time next week. Have a good day as well to everyone.
Thanks, Eugene.
All right.
Thanks, Eugene.
Thank
Thank
you.
you.